Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book. And the last several lectures I've been doing have been on section 5.6 of volume 1, which is on cardinal numbers. And today, this is my 7th video on this sub-series on cardinal numbers. I'm going to talk about a very surprising result, probably one of the most surprising things I ever learned, actually, in math. And that's that there's actually infinitely many sizes of infinity. I mean, I already talked about how the continuum, the number of real numbers is a bigger infinity than the number of counting numbers or natural numbers. So that's two different sizes of infinity. It turns out there's actually infinitely many. And you can use a variation of Cantor's diagonal argument, which I gave a few lessons ago, to prove that, the size of the real numbers was bigger than the counting numbers. You can use a generalization of that argument to prove that if you have any infinite set, actually any set finite or infinite, that its power set is always a bigger set. It has a bigger cardinal. Remember, the power set is a set of all subsets of a given set. Anyway, let's begin. So, so I just have to give you a little bit of background. So, I'm going to talk about power sets. That's how we're going to do this. So, it turns out, let's just think about finite sets first. That's easier. So suppose S is a finite set. I'm going to let S denote an arbitrary set, but first we're going to look at finite sets, just a set with a finite number of elements. And for instance, 5 elements. It's usually easier to think of the elements as the counting numbers, the natural numbers up to that limit. So for instance, a generic set of cardinal number 5 would just be the set whose elements are 1, 2, 3, 4, and 5. Pretty easy set. So what do we mean by the power set? I talked about this earlier. The power set is just a set of all subsets of S. In that case, that would be all the collections of numbers, from 1 to 5, not necessarily all of them. Of course, one of those is the empty set. And it turns out, in this case, you might wonder, what's the cardinality of the power set of S in this case? Well, it turns out it's 2 to the 5th power. It's always 2 to the n. If n is the cardinal number of the set you started with, then the cardinal number of this power set is 2 to the n. And it's pretty easy to see that 2 to the n is always bigger than n. And maybe I should start with a simple example. So, I guess the simplest possible example is the empty set. Empty set is the set with cardinal number 0, has no elements, and its power set is just itself, because it has no elements, so it has no subsets. Or if you like, it's only subsets, the empty set. So that, actually, actually, it has one subset, maybe itself, the empty set. So the cardinal number of the empty set, the power set of the empty set, is actually 1, because it has one element, namely the empty set itself. Maybe that's a little bit of a tricky example. How about just the singleton 1? If you have the set whose only element was the number 1, then I think you can see in that case there's actually 2 subsets. You always have the empty set. The empty set is always a subset of every set. And in this case, you can have the set itself, the set 1. That's the set we started with. So now we have 2 sets in the power set. So 2, the first power is 2. And maybe I'll just go through one more example. How about the set 1, 2? Well, in this case, you can have the empty set, which you can always have. You can have the whole set, 1, 2, or you can have just the element 1 or just the element 2. That's 4 possibilities. 2 squared equals 4. And actually, I think it's pretty easy to see in general. If you have a finite set of cardinal number n, that there are, how do you see there's 2 to the n elements? Well, every subset, just think about the elements. Either an element's in the subset or it's not. And so it's kind of a binary possibility for each element. So there's 2 possibilities for every element. I'm just focusing on a particular subset of the numbers 1 through n. I guess it's easier to look at a concrete example again. 1, 2, 3, 4, 5. One example of a subset of that set is a set whose elements are 1, 3, and 5. I just kind of picked that at random. So 1 is in the set, 2 is not, 3 is in the set, 4 is not, and 5 is in the set. And you can see there's 2 possibilities for every number from 1 to 5, whether it's in the set or not. So we have 2 possibilities for the first element, 2 possibilities for the second, 2 possibilities third, 2 possibilities fourth, 2 possibilities fifth. So the total number of possibilities is 2 times 2 times 2 times 2 times 2, or 2 to the 5th power, 32. That's kind of how you prove that the cardinal number of the power set of any set of cardinality n is equal to 2 to the n. And 2 to the n is always bigger than that. But what's remarkable is that this is also true for infinite sets. And, and we can write, just because we can write 2 to the n as a cardinal number of a power set of a set of cardinal number n, we can do the same thing if S is an infinite set. For instance, if F is a set of positive integers, that's cardinal number is aleph null. So we can write the cardinal number of its power set as 2 to the aleph null. It actually turns out 2 to the aleph null is equal to C. Remember how we did that? Well, I mean, we did sort of like 10 to the aleph null. But anyway, I don't want to get into this too much. But you'll just have to trust me on this. I mean, you can think of this as a definition. So if say K is any cardinal number, finite or infinite, then the cardinal number of its power set we can always write as 2 to the K. You can think of that as a definition if you like. And it kind of makes sense if you think about it, because either an element, whether it's a finite or infinite set, every element of that set is either in or it's not in an element of its power set, a subset. So if you look at all subsets, it kind of makes sense. If you look at every element, it's either in there or it's not. So you have 2 to the K possibilities. Anyway, that's just kind of some overview on this. And maybe I should just talk a little bit. I talk about this bet notation. So the second letter of the Hebrew alphabet after aleph is this funny looking letter called bet, spelled B-E-T-H in English. It's actually Hebrew letters. So, but it looks kind of like a backwards C, kind of a weird looking letter. But anyway, so the notation we use, we say bet naught is equal to aleph null. And bet null is aleph null by definition. It's the smallest cardinal number. And then we define bet 1 to be 2 to the bet naught. So we remember I talked about the continuum hypothesis before. I think I'm kind of jumping the gun here. But if the continuous hypothesis is true, then we said 2 to the aleph null is equal to aleph 1. Well, we're defining bet null to be the same as aleph null, and bet 1 to be 2 to the aleph null, which is 2 to the bet null. So if the continuum hypothesis is true, then bet 1 is equal to aleph 1. I mean, I'll get into generalized continuum hypothesis tomorrow, but anyway, that's just kind of some notation for you. But now I want to present the proof. So we can generalize. This is the remarkable part. I hope you guys can all see this slide, because this is pretty remarkable. Maybe I should put an illustration. It's a little hard to illustrate, but now we're supposed to imagine that S is any set, finite or infinite. I mean, we're really interested in the infinite case. But S is any set of any cardinal number we want. And then I'm going to prove that the power set of S always has a bigger cardinal number than the cardinal number of S. In other words, 2 to the if the cardinal number of S was K, then I'm going to prove that 2 to the K is always greater than K, strictly greater than K. So remember, when we're dealing with infinite sets, the way we prove that one set is bigger than another set is we have to prove there's no bijection from the first set to the second. So that's what we're going to do. And again, this is going to be a proof by contradiction. We're going to use a generalization of Cantor's diagonal argument here. And this is a little bit more abstract than the one I did for proving that there's more real numbers than natural numbers. But it's kind of the same idea. So imagine we have some set S, finite or infinite, And we claim that the power set of S has the same number of elements as S. If that's true, if they have the same cardinal number, then there has to be a bijection from S to its power set. We can give that bijection a name. We can call it, I think in my book I call it, what do I call it, F? F. So we have a function F from S to its power set. And we're assuming F is a bijection. Well, what can we do here? We can, that means that for every subset, let's call a subset of S. We have to give it a name. X. I'm just going to use the letter small x for. X is an element. So suppose X, is this how I want to do it? I want to keep my notation consistent here. Yeah, if X is an element of our set capital S, then f of x has to be a subset, because remember, the power set is a set of all subsets. So then we kind of have two possibilities here. We might, a natural question to ask, does x, the element x, lie in f of x, which is a subset of S, or doesn't it? There's two possibilities. Either it does or it doesn't. So now we're going to be a little clever here. We're going to use a variation of Cantor's diagonal arm, and I'm going to define a particular subset of capital S, which I'm calling D. And the way I'm defining D, I'm saying D is a set of all elements of capital S, such that D does not belong to f of D. Remember, for every subset S, X, either X belongs to f of X or it doesn't. So there's two possibilities. So D is just a collection of all elements where it doesn't. Well, now I can give you a contradiction here. I'm going to... so we can ask whether... how does the contradiction work? I have to get this right. I'm calling this set capital D. F of little d. Remember, little d is a little d is an element, I guess. I have to get this right. Yeah, little d is an element of capital S. So I constructed it. I guess I got my notation backwards here. Capital D I'm defining capital D as a set of all elements X, such that X does not belong to f of X. But now we can ask, and then since we're assuming that this function f is a bijection, that means capital D has to be f of little d for some element little d of capital S. But now we can ask whether we got a contradiction, because remember the way we define capital D, it's a set of all elements such that f of little if x is an element of capital D, that means that f of x is not in the set capital D. But what about f of little d? Remember, little d is an element of capital S. We don't know whether it belongs to capital D or not, but let's assume it does first. If little d belongs to capital D, then capital D is f of little d. That means by definition, by the way we've defined capital D, little d does not belong to capital D. That's a contradiction. And conversely, let's assume that little d does not belong to capital D. Well then, by the definition of capital D, little d does belong to capital D. So we get a contradiction either way. And this is essentially the same as Cantor's diagonal argument, the way I did it last time. It doesn't really look like it, but though we get a contradiction, no matter what our set capital S is. We just showed that there's no bijection between the S and its power set. And we know that the power set has to have at least as many elements as S, because we can take the set of all singletons. The subset of all singletons as a subset of the power set. So we know it has to be a bigger set. So that's the proof. And since you can do this as many times as you want, I mean, we could start with bet naught, which is the same as alf null, and then we get a bigger set. We just proved that bet 1, which is the cardinal number of the power set of of the natural numbers. That one we proved is bigger than bet naught. As a matter of fact, bet 1 is equal to c, the continuum. And we can keep doing this. If we did the power set of the real numbers, which is the set that we get when, that's really the power set of it's isomorphic to the power set of the natural numbers. If we take the power set of that, we're going to get bet 2, and by the same Cantor diagonal argument I just used, bet 2 has to be bigger than bet 1, and so on. So we just proved that bet naught is strictly less than bet 1, strictly less than bet 2, and so on, ad infinitum. So that proves there's infinitely many infinite cardinal numbers. I don't know if you guys can follow the proof I just gave. I kind of messed it up the way I explained it, but you'll have to trust me. You can go through my book and you can go through this proof, and if you really go through it in detail, I think you can convince yourself that it does hold water, that this is an actual proof of the fact that the power set of any set is bigger than the set you started with, which proves there's infinitely many sizes of infinity. Pretty amazing result. Anyway, that concludes my video for tonight. Thank you for watching. Long live math, and I'll see you guys next time. Bye.